Let's say you had an object that was falling due to its own weight. So if we have gravity pointing down and we take positive y to be up, we have this object that in a standard physics 1 approach, we might consider the sum of forces in the y, right, as being minus mg, and that is equal to ma. Ma is acceleration is the time derivative of velocity, so this is dv dt, or you might say m v dot. And so in this way, masses cancel out, and you might come up with an equation of motion, an ODE, for this system as this. And this means that we can integrate both sides and find the velocity as a function of time and position as a function of time of this falling object with no drag. So if we take the integral with respect to time on the left and the right, minus g dt. This is simply velocity as a function of time, and on the right you have minus gt, and we have a plus c constant. Now if we evaluate and say that at time equals 0, the velocity is equal to v naught, then if we take this function, minus gt plus c, and consider that at v of 0, it equals v naught, well, that makes this term go away, and so c is equal to v naught, and we can write the velocity as a function of time in this way, v naught minus gt. And you might recall this from a free fall equation that you've been given. And we can integrate one more time to find the position as a function of time. So velocity t dt, and integrate on the right side, v naught minus gt, and we're going to integrate with respect to time. So on the left, we'll use y, because that's our coordinate system, as a function of time. And on the right, we have v naught t minus 1/2 gt squared, and we have that plus c term. And again, we will say for our initial condition that at time equals 0, t equals 0, this function v naught t minus 1/2 gt squared plus c, at time t equals 0, the position is y naught. In this case, both these terms go to 0, and we're left with c being equal to y naught. So here we have our position as a function of time being y naught plus v naught t minus 1/2 gt squared. And this is a constant acceleration equation, a kinematic equation that you're likely familiar with, specifically for free fall. So this is one of the projectile motion equations you're typically given in, or similar, close to projectile motion equation you're given in a physics 1 class. And this matches a free fall kinematic equation directly. Okay, so given this framework of how we can start with Newton's second law and derive an ODE equation of motion that we can get the respective interesting velocity or position functions as a function of time, what if we considered this object as falling due to its own weight but with a drag force applied to it. So here we'll have our drag force that's applying in the opposite direction. So we would have, I'll do it down here, we would have a free body diagram with mg down and some drag force, which I'll make smaller, force of drag like this, right? And here we can go ahead and take down as y, positive y. So here we have sum of forces being equal to mg minus this force of drag equals ma. And we're going to model this drag force as being proportional to the velocity. So it would be equal to some constant, we'll say k, times the velocity. And you might say that drag force scales with the square of velocity. You might know this. This is true for certain cases, like if you're in a car driving through air, or if you're parachuter falling through the sky. But it turns out that for low Reynolds numbers, certain applications across lots of fields consider linear drag in the case of low Reynolds numbers. So for example, this would be maybe like a sand grain that's settling through some water. That's linear drag. It's not an approximation that is incorrect, but rather that is actually Stokes' law. That's the function that correctly describes the drag. Another one would be a droplet of dew falling or mist, falling through the sky. So it's a very, very small particle, and the velocity is very slow. You can also have something on a very small scale, like a bacteria going through a viscous fluid. That's linear drag. In my prior research, we considered linear drag in the context of an artificially motile nanoparticle making its way via a chemical process, chemical propulsion, through a fluid. So it is appropriate in certain cases with low Reynolds number applications to model drag as linear. So we might consider this particle that we're thinking of with this drag force as being maybe a grain of sand just settling through a glass of water. So to treat this, we want to get this this equation into standard form. So we have mg minus our drag force, which we're going to say is some k coefficient, times v equals ma. And ma is really just the time derivative of velocity, right? So here we have a differential equation, but we want to put it in standard form. So what we want to do is move things around. So I'm going to do m v dot plus k v is equal to mg. And we want the v dot coefficient to be 1. So we're going to divide through the equation by m. So we get v dot plus k over m times v equal to just g. So this is in standard form. This is a first order linear differential equation, and we can solve this via direct integration. So what we can do is one method, we can just we can identify the different terms here, coefficients here. So I'm going to say this is like P of t, and this is like Q of t. And in the direct integration method, we identify a function I of t as being e to the raised to the power of the integral of P of t dt. And then we have the velocity as a function of time, the solution to the differential equation being equal to 1 over I of t times the integral of P t times Q of t dt plus c. This is the method, the formula for direct integration method for a first order linear differential equation. It's likely the first that you come upon when you take your differential equations course. So identifying P of t as this k over m coefficient and Q is just g, we can find that our I of t is equal to e to the k over m dt, or in other words, it's equal to e raised to the kt over m. Now we plug this in. So velocity as a function of time is equal to 1 over this I function, so 1 over e, and one way we can do that a little bit neater is e to the negative kt over m times the integral of p of t and q and t. So p of t is k over m, and oh, whoops, it's not p of t, it's this I of t. There we go. So there we go. So back to this. So q of t is just g, that's a constant, we could put that in front. And then you have I of t, which is this e to the kt over m. And then you're integrating with respect to time, and we have a plus c constant here. Right? All right, so this is equal to, just write this guy out front again, k minus kt over m. And we have mg on the top over k on the bottom, and you're still left with this this e to the kt over m, and then plus c. Or in other words, since some things cancel here, we have just mg over k plus c times e to the minus kt over m, just distributing that through. And then we can do the same thing we did before, saying that v at time t equals 0 of this function, mg over k plus c e to the minus kt over m, when t equals 0, this is equal to v naught, right? So this is, as t goes to 0, this term goes to 1, right? And so we have mg over k plus c equals v naught. And so therefore c is equal to v naught minus mg over k. We can plug that back in to our equation over here and say that velocity is a function of time, our final solution to this is mg over k plus v naught minus mg over k times e to the negative kt over m. And there is our velocity as a function of time. Now this is a particularly interesting one as opposed to position, because we can think about the condition of free fall, of terminal velocity rather. So as time goes to infinity, this situation here, as time goes to infinity, then the drag force, which is scaling with velocity, and velocity is increasing all the time as it falls. So as time goes to infinity, then you should get a situation of balanced forces. The drag force balances and is equal and opposite to the weight of our little sand grain falling down the water. And so therefore there's no net force, and so there's no acceleration. So in the case of terminal velocity, then we have mg being equal to kv, and therefore v, and this is as time goes to infinity, right? So terminal velocity is equal to mg over k. So we have the solution, the function of velocity, for velocity down here as a function of time. So we can take this and see if that matches up to what we find for terminal velocity up above. So terminal velocity check. The limit as t goes to infinity of this expression here, mg over k plus v naught minus mg over k times e to the negative kt over m. As t goes to infinity, remember this negative sign in the exponent there means that it's like it's on the bottom, right? So this is really like the limit as t goes to infinity of mg over k plus v naught minus mg over k divided by e to the kt over m. And here you can see that as t goes to infinity, the denominator is going to go to infinity. And so therefore this entire term is going to go to 0. So the limit as t goes to infinity is just that first, this first term in the equation, mg over k. So that is v as t goes to infinity, or terminal velocity, under this linear drag model. And that matches up above, mg over k, mg over k. So there you go. So this is just kind of an interesting exploration of the edges of physics 1, and bringing into the situation some of the math, both calculus and differential equations, that students often are learning concurrently to physics 1, but sometimes don't always make it into every course. Cross pollution doesn't reach saturation because everybody's at a different level. But here is some just some simple differential equation and calculus applied to a classic kind of physics situation. All right.